Hello again. Today we're going to have a look at how differentiation can work in deriving and proving and validating the formulae for constant acceleration with the CVAT formula. And as well as that, we're going to have a look at a worked example where we use differentiation in the kinematics formulae. So first of all, as ever, there are 4 warm-up questions for you to attempt. 1, 2, 3 and 4. Please have a go at these, pause the video when you're doing so, then press play to see if your solutions match mine afterwards. So without further ado, let's have a look at the solutions to question 1. Question 1, we're dropping a stone. You can assume this is from rest, by the way, if you'd like. So it's just dropped, then it goes into free fall. Model G is 9.8 meters per second squared, and find in terms of t, importantly, an expression for the displacement s. And so just remembering the CVAT formulae, a formula for s, which we're going to use here, let's use that s equals ut plus half at squared. S equals ut plus a half at squared. And what we can say here, we can assume that u is 0. Okay, let's assume that it's just dropped from rest. It's not thrown down, it's not thrown up, it's just dropped. So s, if u is 0, this bit is 0. So just have s equals half at squared. But the acceleration due to gravity is g. And so we can substitute in that a is actually g. And so if we just use a is 9.8, we get that s equals half of 9.8, which is 4.9, then t squared. So s equals 4.9 t squared. For B, there's a couple of CVAT formulas you could have used. What I'd suggest for final velocity v is we do v equals u plus at. But a, as I've said, is g, and u is 0, so this just becomes v equals 9.8 t. So for question number 2 here, so from question 1, the expression for v, we're going to find dv by dt. So we're going to differentiate v with respect to time. So from question 1, what we had is that v equals 9.8 t. Therefore, if we differentiate this with respect to time, 9.8 is just a constant. The t will vanish. So we get dv by dt is 9.8. So just think about what 9.8 represents. That's the acceleration, in particular the acceleration due to gravity. So when we differentiate the velocity here with respect to time, we arrive at the acceleration of the particle. So maybe just think that maybe dv by dt might give us the acceleration. In a similar way for question 3, the expression of displacement in question 1, which I can remind us we had s equals 4.9 t squared. Based off of that, we're going to differentiate s with respect to time for part A. So using this, if we differentiate it with respect to time, ds by dt, the power of t drops by 1, and the old power comes to the front and multiplies the coefficient. So this 2 multiplies the 4.9 to give us 9.8. The power of t becomes t to the power 1, which is just t. So ds by dt is 9.8 t. But remind ourselves of what we got from question 1 and question 2. This is the velocity. So it seems that when we differentiate the displacement with respect to time, we end up with a velocity. For part B, we're going to find the second derivative. We're going to differentiate this again. And so d squared s over dt squared, we're going to differentiate this expression again with respect to time. The function of time, for t here, the power drops from 1 to 0. T to the power 0 is just 1. So in effect, the t just vanishes, and we get 9.8. And remember what 9.8 is. That's the acceleration due to gravity. And so we should be building up a picture on our heads now. If we differentiate the displacement, we get the velocity. When we differentiate this velocity, we arrive at the acceleration. We're going to clarify this in the next steps in this video. Question 4. And this is a formula for constant acceleration, which we saw in question 1. S equals ut plus half at squared. This should now be familiar to you. We're going to find the first and second derivatives of this with respect to time. And so if S is this, ds by dt, differentiate this with respect to time, this here, u is just a constant, u is the initial velocity, whatever that might be. So if we differentiate this bit, ut just becomes u. Whatever a is, for example, a might be g, half a, as a is just a constant. So we have half a, and the t squared, when we differentiate t, t squared becomes 2t. So we have u plus half a multiplied by 2t, but this can then be neatened up. Half times 2 just gives us 1, so we just have a t. But remember, from VC that formula, we have v equals u plus at. So it would appear that ds by dt is one and the same thing as v. And it actually is. This is just a nice way of proving it to you. We now need to find the second derivative, so we now need to do d squared s by dt squared. So if we differentiate this again, u, as I said, is just a constant. It's the initial speed, whatever that happens to be. So this disappears. A, modelled as before with constant acceleration, that's just a constant. So the power of t drops to 0, so we're just left with a. And so when we differentiate displacement twice, we get the acceleration. This is actually a lovely result we're going to use time and time again. Moving forward to the main bit today, just as we've seen in this warm-up, if we define velocity as change in speed over change in time, as a derivative we have ds by dt. And so the SI units of speed, and velocity in particular here, is ms minus 1. In the same way, like I'm saying here, we can understand that acceleration is the rate of change of velocity with respect to time. So it's the change in velocity divided by time. In derivative notation, it's dv by dt. And the units of this are ms minus 2. I'm just going to show you now how the GCSE concepts relink to these derivative concepts. So if we just go back and use something more familiar, for gradient, for example. For gradient, between two distinct points first of all, so the distance between these points might be quite big. For gradient, as you should know, that's the change in y over change in x. Delta y, delta x. As these 2 points get closer and closer together, this change becomes a small change. So we have delta y over delta x with a small lowercase delta. Then in the limiting case, where these 2 points become closer and closer and become 1, we go from something which is macroscopic to something which is a calculus limit. And so this delta becomes d. So we go from triangles to deltas to dy by dx. This is hardly rigorously mathematical, but I just think it's a nice link for you to see. Similarly, velocity, between any 2 points, the velocity is just change in displacement over change in time. Make these 2 points between the times closer and closer, we get this, and then after, delta s over delta t becomes ds over dt in the limiting instantaneous case. Acceleration, same way, dv over dt. We can arrive at this using these following steps. So we may as well fill this in now, just as we had before. And we had ms minus 2, and here we had ms minus 1. Let's have a look at an example. So question 1 here, we've got a particle moving along the x-axis. After time t seconds, its displacement is given by this function here. For part A, we need to find the velocity when time equals 3. Well, the velocity, just going to section the page off so I can just do it all in one. Velocity is when you differentiate the displacement. So we can find the velocity by differentiating the displacement with respect to time. So if we differentiate this function with respect to time, the old rules apply. The powers of t drop by 1, the old power goes to the front. So t4 becomes 4t cubed minus 32t just becomes minus 32. Any constant terms vanish, so this plus 12 vanishes. So that's the general expression for the velocity. For part A, we want to find the velocity of p when t is exactly 3. So for part A, we can say that when t is 3 seconds, we're going to have that dx over dt is 4 lots of 3 cubed minus 32. So using your class whiz or whatever, 3 cubed is 27, 4 times 27 gives you 108, and 108 take 32, that's going to give us 76 meters per second. For part B, the value of t for which p is instantaneously at rest. So for part B, when it's at rest, velocity is 0. And so v is going to be 0, just repeating what I've said here, when the velocity function is equal to 0. So we want to solve this equal to 0. So when is 4t cubed minus 32 equal to 0? It turns out this is actually going to be very simple to solve. So if we add 32 to both sides, we get 4t cubed equals 32. We can now divide both sides by 4. So t cubed is going to be 8. Cube root both sides. Cube root of 8 is 2. And so the velocity is going to be instantaneously 0 when t is equal to 2 seconds. Lastly, part C, find the acceleration of p when t is 1.5. Well, the acceleration is when we differentiate the velocity. So the acceleration is going to be dx by dt, again differentiated. So it's going to be d squared x over dt squared, which I'm just going to remind us, it's the same as saying it's dv over dt. So we're just differentiating this function of displacement again. So we're going to differentiate this now. And so the power of t comes to the front, multiplies a 4. 4 times 3, we're going to get 12. T cubed becomes t squared. And this constant term here, the minus 32, will just vanish. And so we're going to have that the acceleration is 12 multiplied by the time squared. So for part C, the acceleration when the time is 1.5, we can just sub in t equals 1.5. So when t equals 1.5, we're going to have that the acceleration is 12 multiplied by 1.5 squared, and that gives us exactly 27 meters per second squared. So I'm going to keep this video short today. That'll do us for now. What you need to do, as ever, is apply this yourself. Just listening to me isn't going to get you very far. I'd like to imagine I'm incredibly interesting and incredibly inspiring, and you can learn the whole world by listening to me, but it's just not the case. You need to do the work yourselves. So hopefully that video has been useful, but apply what you've learnt now from the notes and this video. Go to page 185, exercise 11b, and attempt all the questions. You know the drill by now. Self-assess using the answers at the back. If you're not sure where you've gone wrong, try again. If you're still not sure, email me or leave a comment in the comment section and keep plugging away. Do not give up. So until the next video, I'll see you again. Thank you very much for listening and good luck with these questions. Cheers.